Today we're going to talk about the beginning of calculating centroids. And the first thing that we need to do when we're thinking about like a centroid, and a centroid is basically just a common term for a center of mass, either like a center of gravity, center of mass. It's called several different things. But what we're really looking for is the distribution of an object and where that object's center of mass is. There's a couple of reasons why we would want to do that. One, you can balance things on the center of mass. So you've seen situations where people have taken like brooms or hammers or things like that, and they've tried to balance them on their fingers. People do this with like ruler sticks all the time. It's easy to do when it's a ruler stick because it's the same amount of mass on both sides. So it's really easy to see that the centroid or the center of mass is in the center. But that's not always true depending on every shape you have. So if somebody was taking a broom and lifting it up, then that broom is obviously heavier on the broom end than the handle end. So you've got a lot of handle sticking out for a balancing act, and then you've got a heavy broom side, so it's not really a lot of mass on the other side. So the centroid is not located in the smack dab middle of that position or of that broom. So we have to sometimes do a little bit of calculations in order to find out what those centroid locations are. So we're going to take a look at a couple of easy examples. We're going to take a look at a right triangle, we're going to take a look at a circle, and we're going to take a look at a rectangle. Actually, you know what? I misspelled that. So it's not, we're not actually going to look at a circle. We're going to specifically look at half of a circle. So we're going to look at a semicircle. So the circle is really easy. That's why I say that, because if you're looking at the center of mass of a circle, if you draw it out, it's pretty intuitive to see that the center of mass of a circle is going to be right in the middle of the circle itself. And this symbol that you see here with the circle, with the shading in on the top left and the bottom right, this is usually the symbol that denotes where the centroid or the center of mass of an object is normally located. And in this case, there's a couple of cheats that we can do. And the cheat with the circle is, you've got lines of symmetry in the X and the Y direction. So if you cut a circle in half, either in the X direction or the Y direction, there's an equal amount of stuff on the left side and an equal amount of stuff on the right side. So because of that, that ends up being a symmetric object, and therefore the center of mass or the centroid is located right in the middle. Okay, a semicircle we're not so lucky on, but we're just going to know these in order to get them to actually work out. So let's see what we've got here. Let's do the right triangle first. Actually, you know what? Let's do the rectangle first because that's the easiest one to do, and it's probably the easiest one to reason with people to see what it actually looks like. So I'm going to draw a rectangle, and on this rectangle, the very first thing we need to do when calculating the centroid is we need to determine where a reference point is. So I'm going to put a little cross here over here. I'm going to write O for the origin. So this is our reference point. In math, we call it an origin. And in engineering, we're just going to call it like a reference location. So this reference location is where we're going to locate the centroid. And the rectangle has the same cheat that we can use. It's symmetric. So if you were to cut the rectangle in half on the y-axis, then you would say that, well, okay, this has a centroid, or this has to have the same amount of stuff on the left and the right-hand side. So the x position of the centroid is going to be right about here on the line of axis. The same thing happens horizontally too. If you make a line on the x-axis, then you've got the same amount of stuff above that line and the same amount of stuff below that line. So therefore, your centroid has to be located in the middle right here of the object. So in this case, if you're looking at it from the origin, and this is where it gets important because, the base of the rectangle, let's just call that B, and the height of the rectangle, let's just call that H. The reference point is going to be halfway across the base, so I'm going to denote where the centroid is by writing the x bar and the y bar. So I'm going to say that x bar, and whenever you say x bar, this is basically just saying the average of where all of the mass is distributed through the object. The bar on top usually means average. In math, it means average. So that's what we're talking about here. We're talking about like an average of where all the stuff is in the x direction. And in this case, the average is going to be located at b over 2. So it's half of b, and I'll write it as b divided by 2. Okay, and the y bar is going to be, this is going to be the average of where all of the y stuff is. This is going to be located at the height divided by 2. So that's going to be h divided by 2. And this is in general how we calculate centroids. We use these simple shapes because whenever we start calculating the centroids of more complicated objects, we're going to find out that these more complicated objects are more often than not just broken up into simple shapes and calculated that direction. If you go through a more rigorous study, then you're going to learn that if the shapes don't play nice, then you're going to have to use calculus to get through that. But this video is totally only for just taking simple shapes and adding them together. This is for high school, basic engineering 101. Okay, let's go for the next one. Let's go for a semicircle. So I'm going to draw out a circle that's been cut in half. So I'm going to draw a semicircle, or at least as close as I can to a semicircle. It looks kind of more like a water drop. But you know what? It'll totally work. And we can kind of make the same argument here. For this semicircle, you can cut it in half this way. So I can go, you know what? There's a line of symmetry about right here. And so therefore my x bar, if I'm making a reference point right here, my x bar is going to be at half of the base. But in the case of a semicircle, we don't call it a base because it's a circle. So we're going to say that our x bar is going to be located at the value of the radius, or half of the diameter. So we normally just say that the x bar is equal to r, the radius. Okay. Let's see here. And if I look at the, I can't really cut that top part in half because if I go straight at the halfway point, it becomes pretty obvious to me. So like if I cut it right here, it's pretty obvious to me that there's more stuff down below than there is up above. So I can't really make this argument anymore. I know that my centroid location for the y direction is going to be a little bit lower than when we started. So it's probably going to be somewhere more like around here. And in that case, it turns out that the y-bar location, and we could average this up together, but it's going to involve calculus, and the answer is no. Just take my word for it, or go look at another video. The y-bar value, or the average value of the mass in the y direction for a semicircle is going to be 4 times the radius divided by 3 pi. Okay, and you're going to kind of see this 4/3. This 4/3 should kind of look familiar to you. That's going to be like the volume of a sphere. So that 4/3 shouldn't be too surprising to kind of see this in the equation for the average distribution. It shows up a lot whenever you're dealing with circles, the 4/3. Okay, and that would be the average of the x bar and the y bar. So if you were trying to find the centroid location, say it had a radius of 3, the x bar would be 3, so you'd go over 3 units to this direction. And then the y bar, you would go up 4 times 3 divided by 3 pi. So that's going to be 4 divided by pi. It's just a little bit over 1 unit up. So it'd be about right here-ish, which is a little bit below the halfway point. And which makes sense because the bottom of the semicircle is going to be heavier than it's going to have more mass on it than the top of the semicircle. And let's talk about let's see what's left, the right triangle. And this one's not nearly as bad as the circle because we don't have to deal with pi. So, but we are going to have to deal with a right triangle. So I'm going to move this down. Let's draw a right triangle. And let's get these 3 simple shapes out of the way so we can use these 3 simple shapes. And we can also calculate the centroids of those 3 simple shapes using a couple of methods. All right, so if we've got, let's see, a triangle, I'm trying to look and see if I can cut this in half in any location, and it looks like I really can't cheat in either case because if I try to cut it in half, it's not symmetric. It doesn't have a line of symmetry about it. Now, some people would argue that you could take a line of symmetry and like cut it in half down the middle, but I would say that's not a good idea because this is going to work for any right triangle. So if your triangle looks like this, you can't cut it in half down the middle. That's not going to work the same way. If it's got like a really long one of the legs is really, really long, that's not going to work out. So it might work out for you in isosceles right triangles, but it doesn't work in all right triangles. But if we just calculate the centroid using the x bar and the y bar for this simple shape, if you make a origin point, then the x bar and the y bar is going to be at 1/3 of the base and 1/3 of the height. So the x bar is going to be located at the base divided by 3, or a third of the base. So that'd be about, right here, if you're taking this number on this line and cutting it into thirds. And the y bar is going to be at the height divided by 3. So it's going to be h divided by 3. So it would be somewhere about right here. So if you're looking for the centroid of a right triangle, it's going to be about in that location. In the case of this one, I can take this right triangle and, well, I'm talking about the one on the right that's got the really long leg. I can go about a third of the base, and I can go about a third of the height, and your centroid is going to be located at this location if you've got your origin point over here. In general, for right triangles, you want to put your origin point, and for any of them, you want to put your origin point on the base. So like you don't want to make your, if it's a semicircle, you don't want to put your origin point like at the very tip top of the circle and be like, look, I'm special. You're just giving yourself heartache at this point. You really don't want to do that. For the cases of the way that I do it, I always try to make my centroid locations, if I can, or sorry, my reference point locations, if I can, at the bottom left of the shape itself. Now, sometimes the triangles are flipped over backwards, and I can't do that. So, if I were to have a right triangle that looks like this, I'm not just going to sit there and go by that rule and be like, bottom left is the way to go. I'm going to say, you know what, the base of the right triangle is going to be located over here. So I would make the origin this way, and I would just move my locations to the left and then up instead of going to the right and then up. Okay, these are the three formulas that we're going to need, and we're going to use these. So I would highly suggest that you keep these, ooh, as I destroy the over 2, I would highly suggest that you keep these handy. So I would keep the x bar and y bar for a rectangle. I would keep the x bar and the y bar for a semicircle. You never have to actually calculate these. You can just use these formulas to actually get the centroid values. There we go. I would highly recommend we keep all of these x bars and y bars for a semicircle, for a right triangle, and for a rectangle, and keep them near and dear to you. And I'll show you guys what we're going to do with them and how to use them in the next video. Have a great day, and I'll talk at you later.